All right, so hello again. In this section, we want to take a look at non-homogeneous linear constant coefficient equations. All right, so we saw what to do if we had homogeneous equations, where the one side of the equation was 0. Now, what if it's non-homogeneous? All right, so what this means is we want to solve an equation of the form a y double prime plus by prime plus cy is now some function of x instead of 0. Now, the general idea is what we're going to do is we're going to solve the equation we solved before, the homogeneous equation. We'll call that y sub h. And then we've got to find what we call the particular solution, yp. And so then the general solution is given by y equals y sub h, the homogeneous solution, plus y sub p, the particular solution. Now, how we find the y sub p, there's a couple of different ways. There's a couple of methods. One method is called undetermined coefficients. It only works for certain forms of the function f of x, where we make an educated guess on the form, and then we see what happens. And then there's variation of parameters. It works in general, but we have to solve a fairly complicated system of equations, and then we have to do some integrations, and the integrals aren't always nice. So we'll see briefly both, we'll work more with undetermined coefficients, talk briefly about variation of parameters, and see one example of it. All right, so let's see an example. We're going to solve using undetermined coefficients, and so let's see. So here is, we're asked to solve y double prime plus y equals 3e to the 2x. So the first thing we do is, we find what we call the y sub p, the y sub h. We find the homogeneous solution. So we're going to solve y double prime plus y equals 0. All right, so we learned how to solve this already. We make the substitution, y equals e to the rx. We get the auxiliary equation, r squared plus 1 equals 0. This implies that r is positive or negative 1. And so what that tells me is the y sub h is c1 cosine x plus c2 sine x. All right, second, we need to find the y sub p. And for undetermined coefficients, we make an educated guess. We are adding a function to its second derivative, and we get back some function involving an exponential. So the guess we're going to make is, so I'm going to assume that y sub p is a e to the 2x. Why? Because the result has that general form. It's some multiple of e to the 2x. I'm going to guess that it fits this form. Now let's see if it works. All right, so if y is ae to the 2x, then y prime would equal 2a e to the 2x, and y double prime would equal 4a e to the 2x. Substituting, y double prime 4a e to the 2x plus y a e to the 2x is equal to 3e to the 2x. Right? Y double prime plus y equals 3e to the 2x. So then 5a times e to the 2x is equal to 3e to the 2x. And for this to be true, this implies that 5a must equal 3. And so then a is 3/5. And so what this tells us is then y is equal to y sub h, the homogeneous solution, plus y sub p, the particular solution. And so then y is equal to c1 cosine x plus c2 sine x. And then the particular solution was a e to the 2x, where a is 3/5, so plus 3/5 e to the 2x. And we can see why this works, why this must be the solution. if I substitute this in, right, if I substitute this equation into the differential equation, then notice the c1 cosine x plus c2 sine x, that will give me, upon its second, adding it to the second derivative, that'll give me the 0, right? That'll give me 0, and then substituting the 3/5 e to the 2x in and adding it to its second derivative and going through all that, that will end up giving me the 3 e to the 2x. So this is the general process for solving non-homogeneous equations. We have to find the homogeneous part, homogeneous solution, and the particular solution, and then we add them together. Alright, so let's see another example. Here we're asked to solve y double prime plus y is 4x cubed. Alright, so notice that the homogeneous part, the y double prime plus y, if we were to solve for yh, right, we'd have y double prime plus y equals 0 again, and that's the same solution, that has the same solution as what we saw in the previous example, and so again the y sub h is c1 cosine x plus c2 sine x. So let's focus on the y sub p. Now, here, if we focus on the right-hand side, it's not exponential, it's polynomial. And so the assumption we make is that the y sub p is also a polynomial, and we assume that it has the same degree as that function, the 4x cubed. So what we're going to assume is, assume that y sub p is a 4th degree polynomial. And so I'll write it as a 3rd degree polynomial. Ax cubed plus bx squared plus cx plus d. Alright, so then the y prime would be 3ax squared plus 2bx plus c, and the y double prime would be 6ax plus 2b. We substitute y double prime 6ax plus 2b plus y, ax cubed plus bx squared plus cx plus d, and this must equal 4x cubed. Now we sort of look at both sides of this equation, and we have to make the coefficients work, right? So if we sort of think about this, let's focus on maybe the x cubed. So let's see, I've got 4x cubed on the right, and I have ax cubed on the left. So a must equal 4. Now let's focus on x squares. Well, hey, there's no x squared. There's 0x squared on the right, and there's bx squared on the left, so b must equal 0. Now let's focus on the x. How much x do we have on the right? Well, I've got 0x. Maybe I should have written in that 0x squared term here as well. I've got 0x on the right, and I have 6a plus cx on the left. So I have 6a plus c must equal 0. Well, I know a is 4, so then this implies then that 24 plus c must equal 0, and so then c must equal negative 24. Alright, and finally, how about the constant? Well, again, I have plus 0 on the right, and I have 2b and plus d on the right. So 2b plus d must equal 0, and I know b is 0, so that means that 0 plus d is 0, and so therefore d is 0. Alright, so now putting this together, remember our general solution then is y is equal to y sub h, so c1 cosine x plus c2 sine x, plus the particular solution. And the particular solution, remember the particular solution was ax cubed plus bx squared plus cx plus d, And now we know that A is 4, and B is 0, C is negative 24, and D is 0. So substituting, that gives us plus, so then we would have 4x cubed minus 24x. And that is the general solution of this differential equation. All right, here's a third example. Here again we have y double prime plus y, but now it's equal to cosine 2x. All right, so again, the y sub h will be c1 cosine x plus c2 sine x. All right, because the non-homogeneous part has not changed. All right, now for the particular solution, y sub p. All right, so now we focus on the f of x, and now it's of the form cosine 2x. All right, well, it's not exponential and it's not a polynomial. So this is a new form. All right, so if we have a form that involves a sine or a cosine, what we do is we make the assumption that it can be a combination of sine and cosine. And so what I'll write is the y sub p, the assumption is it's I'll write a cosine 2x plus b sine 2x. So we can't forget that if we have, for our function, if we have that cosine or a sine 2x, we have to involve both of them. All right, so then y sub p prime, all right, so calculating a derivative, we'd have negative 2a sine 2x plus 2b cosine 2x. And calculating the second derivative, let's see, I'd have negative 4a cosine 2x and a minus 4b sine 2x. Substituting into the differential equation, I would have then negative 4a cosine 2x minus 4b sine 2x plus y plus a cosine 2x plus b sine 2x, and we need that to equal cosine 2x. All right, so like we did with the previous exercise, we sort of look at the coefficients. The terms have to match. So let's look at the cosine terms. On the left, I have a negative 4a cosine 2x and an a cosine 2x, and on the right I just have a cosine 2x. So that tells me that negative 4a plus a must equal 1, right? There's a 1 cosine 2x here. So negative 3a equals 1, and therefore a is negative 1/3. Let's focus on the signs. I have negative 4b plus b is 0. And so therefore b is 0. All right, and we can then put together the general equation. Y equals the y sub h, c1 cosine 2x. No, sorry, it was just x. c1 cosine x plus c2 sine x. And then we have the y sub p, and the assumption now, right? Y sub p is a cosine 2x plus b sine 2x, and I now know that a is negative 1/3 and b is 0. So plus, well, I guess really minus 1/3 cosine 2x. All right, so those are some of the basic ideas of undetermined coefficients. Now, unfortunately, it really only works in these sorts of cases where the function, the f of x, is either an exponential, a basic exponential form, a polynomial form, or a sine or a cosine, or some combination of those. So now let's see another example. All right, so let's try to solve y double prime minus 4y prime plus 4y is equal to e to the 2x. All right, so first let's find the y sub h. So we need to solve y double prime minus 4y prime plus 4y is equal to 0. And so we make the standard assumption that y is of the form e to the rx. We get the auxiliary equation. r squared minus 4r plus 4 is 0. And you'll notice that this factors as r minus 2 squared. So that gives us r equals 2, but multiplicity 2. And so what this means is, remember, then the form of the solution, the y sub h, would be then c1 e to the 2x plus c2x e to the 2x. Now, we need to find the y sub p. And since our function, our f of x, has the form e to the 2x, we might say, okay, well then the y sub p should equal a e to the 2x. But it can't. Y sub p can't equal a to e to the 2x. And so maybe I'd like to think, I hope you pause now and think, why can't the y sub p equal a to e to the 2x? Why won't it work? Hopefully, you thought, well, wait a second, I already have an e to the 2x term. And so then this is not linearly independent to the y sub h. So then what do we do? Well, it turns out that then we say, well, okay, just multiply it by x. And it turns out it works. So our second guess would be that y sub p is equal to a x e to the 2x. But again, now look, I've already got an x e to the 2x. So again, this is not linearly independent to the homogeneous solution. So we multiply by x again. All right, so y sub p is equal to a x squared e to the 2x. And that's what we're going to use. All right, so this doesn't work. This doesn't work. We've got to go with our third guess in this case, because it's now linearly independent to the solutions from the homogeneous solution. All right, so we calculate derivatives. Yp prime, so let's see, we have a, and then let's use a product rule here. So I'd have an x squared times 2 e to the 2x plus 2x e to the 2x. Or, let's see, did I simplify that out? Yeah, I multiplied it out. So let's see, then this is 2a x squared e to the 2x plus 2a x e to the 2x. And I still got to calculate the second derivative, right? y sub p double prime. And if you go through the product rule again, let's see. So we'd have 2a, and I'd have an x squared times 2 e to the 2x plus 2x e to the 2x. And then I'd have a plus 2a. And then the derivative of x e to the 2x, I'd have an x times 2 e to the 2x plus, let's see, 1 times e to the 2x. So this is really messy. Got to be careful of your product rule here. So let's see now. I have what? 4a x squared e to the 2x plus 4a x e to the 2x plus another 4a x e to the 2x, and then plus a 2a e to the 2x. So yp double prime is 4a x squared e to the 2x plus 8a x e to the 2x plus 2a e to the 2x. Now we have to substitute those in and actually solve for a. All right, so substituting the yp double prime, which was this, yp double prime. So let's see, I've got 4a x squared e to the 2x plus 8a x e to the 2x plus 2a e to the 2x minus 4y prime, and y prime was 2a x squared e to the 2x plus 2ax e to the 2x plus 4y, and y was ax squared e to the 2x. That was my assumption. And I need this to equal e to the 2x. Oof, this is a mess. All right, let's see if we can clean this up any. So let's see. Let's look at the x squared terms. I've got a 4ax squared e to the 2x. I have a minus 4 times 2ax e to the 2x, and I've got a plus 4 times ax squared e to the 2x. So I've got 4a minus 8a plus 4a, and that's all times x squared e to the 2x, and so those go to 0. All right, that's okay. Now let's look at these. Let's look at the x e to the 2x terms. I've got an 8ax e to the 2x and a minus 4 times 2ax e to the 2x. So that's good as well. Notice, so that's an 8a minus 8a x e to the 2x. So that's going to go to 0. Okay, so now finally these last terms, I've got a 2a e to the 2x must equal e to the 2x. Right? 2a e to the 2x must equal e to the 2x, and so then 2a must equal 1, and so finally a must be 1/2 after all that. Okay, write the equation. So then y is equal to y sub h, c1 e to the 2x plus c2x e to the 2x, and then plus the y sub p, which is then 1/2 x squared e to the 2x. So we have to be careful about, we still need linear independence of solutions. So we still have to be aware of that. All right, so a quick recap of general forms of y sub p. If our function is a polynomial of degree n, our assumed y sub p is also a polynomial of degree n. So if my f of x was, say, 9x to the 5th plus 7x squared, let's just say something like that, then my form of y sub p would be ax to the 5th plus bx to the 4th plus cx cubed plus dx squared plus ex plus f. Or something else similar, using whatever letters you want. If we have an f of x that is of a trigonometric form, a basic trigonometric form with either a cosine or a sine, k cosine nx or k sine nx, or a sum of those. So if I had something like k cosine nx plus l sine nx, then my assumed form is the sum, and the key thing that some students forget is it's got to be the sum of both of those terms, an a cosine nx and a b sine nx. So a quick example, if I had, say, and this is similar to one we saw, if my f of x was -2 cosine 10x plus 3 sine 10x, then my assumed solution is a cosine 10x plus b sine 10x. I've got to remember both of those terms. And the first case we saw, and probably simplest, is if our y sub p is of a basic exponential form, our assumed solution is also a basic exponential form. And I won't do an example of that one. That was the very first example we saw. All right, and if our function has a sum of those pieces, a polynomial, say plus an exponential like we see here. So here I've got the function is x cubed plus e to the 3x. My assumed y sub p is a sum of those two pieces. So for the x cube, I would assume an ax cube plus a bx squared plus a cx plus a d. And then for the e to the 5x, a lot of students will want to do this, a to the 5x. But we have to use a different letter. Don't use the a, use some other letter. So I'll use a capital E. Or something else, right? But we don't want to repeat any of the coefficients. And similarly, if we have a product instead, so here I have x cubed e to the 5x, we multiply. So my y sub p would be ax cubed plus bx squared plus cx plus d times, and now here's the thing, I only need the e to the 5x. I don't need another constant, because if we think of the distributive property, I'd be multiplying, right? I've got this a x cubed times an e to the 5x. Well, if I put a constant in here, if I do put, say, an e in here, then I have a times e, which is a constant again. So I don't need another constant here. It's not incorrect to put it, it's just unnecessary and it complicates things. So I would just write ax cubed plus bx squared plus cx plus d times e to the 5x, and that would be sufficient. The other technique, so we've seen what we call the undetermined coefficients method. And unfortunately, it only works in those specific cases. There's another technique called variation of parameters. It works more generally. It is a bit tougher, though. What it does is it requires an assumption, and we still need to find the y sub h. So we still find the y sub h first, and we assume that then the y sub h, so we have the y sub h is some c1y1 plus c2y2, where y1 and y2 are linearly independent. So then what we do is we say, well, then our particular solution can take this form, u1 y1 plus u2 y2, for some functions u1 and y1, u1 and u2. And if we then substitute and do a bunch of work, we end up with a system of equations that looks like this. It says u1 prime y1 plus u2 prime y2 is 0, and u1 prime y1 prime plus u2 prime y2 prime is then that f of x. And we can then solve this system of equations for u1 prime and u2 prime, and then hopefully we can then determine the u1 and the u2 through integration or antiderivatives. This is a messy process, and again, then finding the antiderivatives is usually the difficult part of this. So it will work, but it's not always pretty. So let's solve again the equation y double prime plus y prime is equal to 3e to the 2x, but now let's use this variation of parameters method. Alright, so recall that the y sub h for this equation was c1 cosine x plus c2 sine x. And so what I'm going to take from that is the y1, let's take that to be the cosine x. The y2, we'll take it to be the sine x. Let's go ahead and calculate the derivatives of these. The y1 prime is negative sine x, and the y2 prime is cosine x. So from this, we build the system of equations. All right, and that was on the previous slide, and the system of equations was u1 prime times y1. So I've got u1 prime times cosine x plus u2 prime times y2 sine x must equal 0, and u1 prime times the derivative of y1, so negative sine x, plus u2 prime times the derivative of the sine x, so cosine x, must then equal the 3e to the 2x, the f of x. Now this is a system of equations, and my goal is I want to maybe isolate the u1 prime or the u2 prime and solve then for u1 or u2. So you can still use any substitutions or eliminations that you want. So what I'm going to do is I'm going to multiply the first equation by sine x and the second equation by cosine x. Alright, and so what that gives me then is, let's see, I've got a u1 prime sine x cosine x plus a u2 prime sine square x is 0. And then I've got a negative u1 prime sine x cosine x plus a u2 prime cosine square x is equal to 3e to the 2x cosine x. And now adding these equations together, right, notice I have an elimination here. Adding these equations together then gives us u2 prime times sine square x plus cosine square x is equal to 3e to the 2x cosine x. And if you remember your basic Pythagorean identity, then sine square x plus cosine square x is 1, and so I now have u2 prime is equal to 3e to the 2x cosine x. So then u2 would be the antiderivative of 3e to the 2x cosine x, and we'll throw in the dx. And if you saw these integrals in calculus 2, you're going to have to use parts twice. Use integration by parts twice. And we find that u2 is, I'm just going to copy this from my note sheet, I'm not going to go through this process here. We find that the u2 ends up being 3/5 e to the 2x sine x plus 6/5 e to the 2x cosine x. So I now know u2, and now I can use that to find u1. Alright, so let's use the fact that u1 prime cosine x plus u2 prime sine x must equal 0. That was our first equation of the system. And I now know that u2 prime, so use this line right here, I know that u2 prime is equal to 3e to the 2x cosine x, and that's being multiplied by sine x. So notice I made that substitution for u2 prime, and that's equal to 0. And if we solve for the u1 prime here, u1 prime would then equal negative 3 e to the 2x sine x. And so again, then u1 would equal the antiderivative of negative 3 e to the 2x sine x dx. And again, if we use integration by parts twice, we find that u1 is, I'm just going to again copy from my note sheet here, u1 is then 3/5 e to the 2x cosine x minus 6/5 e to the 2x sine x. Alright, so we're almost there. Remember that the assumption previously was that the y sub p was then u1, y1. So u1, 3/5 e to the 2x cosine x minus 6/5 e to the 2x sine x times y1 cosine x plus u2 y2, 3/5 e to the 2x sine x plus 6/5 e to the 2x cosine x, and y2 was sine x. So let's see if we can simplify this any. Alright, so yp, let's see, we would have, what, a 3/5 e to the 2x cosine square x minus 6/5 e to the 2x sine x cosine x plus 3/5 e to the 2x sine square x plus 6/5 e to the 2x sine x cosine x. So notice something nice happens here, right? This minus 6/5 e to the 2x sine x cosine x plus 6/5 e to the 2x sine x cosine x. Those terms go to 0. And now look at what's remaining. I have a 3/5 e to the 2x times a cosine square x plus a sine square x. And again, there's our Pythagorean identity. That's 1. And so y sub p is 3/5 e to the 2x. And we get the same result that we got earlier using undetermined coefficients. So finally, y is equal to y sub h, which was again c1 cosine x plus c2 sine x plus the y sub p, which is 3/5 e to the 2x. So this variation of parameters idea, it works. It can be much more difficult, right? But in some cases, it might be the only technique that will work. And so you have to be aware of it. All right, so let's look at one more example. And again, we'll use variation of parameters to solve this equation. We have y double prime minus 2y prime plus y is equal to e to the x natural log x. See here, I can't use undetermined coefficients. That natural log x in there throws things off. I just can't do it. So I have to, so if I'm going to solve this, my other option is variation of parameters. All right, so let's try it and let's see what happens. All right, so let's first find the y sub h. Y sub h. All right, so solving the homogeneous part, we'd have r squared minus 2r plus 1 is 0, and that factors as r minus 1 squared. So we have r equals 1, but with multiplicity 2. So my y sub h is then equal to c1 e to the x plus c2 x e to the x. So there's the y sub h, which means that I'll take the y sub 1 to be e to the x. I'll take the y sub 2 to be x e to the x. The y sub 1 prime then is also e to the x. And the y sub 2 prime, you'd have to use a product rule here. So let's see, this is x e to the x plus 1 e to the x. And so I can write that as x plus 1 e to the x. Let's write the system of equations. All right, so now variation of parameters. All right, so I've got u1 prime e to the x plus u2 prime times x e to the x is 0. And I have u1 prime, again, e to the x, because that's the y1 prime, plus u2 prime, and then I'll have the x plus 1 e to the x. And this has got to equal e to the x natural log x. So there's the system of equations, and now let's see if we can do any solving with this. So here's what I notice. Look at these terms. I've got a u1 prime e to the x, and I've got a u1 prime e to the x. So I've got it in both equations. So what I'm going to do is let's subtract the equation. So I'm going to take my first equation, I'm going to subtract the second equation. So then this gives me equivalently, so let's see, those terms go to 0. I'd have u2 prime times x plus 1 e to the x minus x e to the x, and that's got to equal e to the x times the natural log of x. So x plus 1 e to the x minus x e to the x, so I now have u2 prime times e to the x is e to the x natural log x. The e to the x's reduce out, and u2 prime is natural log x. So then u2 is the antiderivative of natural log x, and this is something that you hopefully saw in calculus 2. It's you use an integration by parts, and we find then that u2 is equal to x minus 1 times the natural log of x. And you can verify this by applying an integration by parts. Alright, so I've got the u2. Now I've got to figure out u1. Again, let's go back to the first equation of the system. And I know that u1 prime e to the x plus u2 prime x e to the x is equal to 0. And I know that the u2 prime is the natural log of x. So I've got u1 prime e to the x plus natural log x times x e to the x is equal to 0. And if we solve this for u1 prime is then equal to negative x natural log x. And so then u1 is equal to the antiderivative of negative x natural log x dx. And we again apply an integration by parts. And u1 is then, I'm taking this from my notes here, u1 is then negative 1/2 x squared natural log x plus 1/4 x squared. Alright, so what do I now know I've got the y sub h, and I've got the u1, where the u1 is here, and the u2 is here, and so I can start putting things together. Oops, sorry about that, went a little too far. Alright, so remember that then the y sub p is u1 y1 plus u2 y2, and so then u1 is negative 1/2 x squared natural log x plus 1/4 x squared times y1, and our y1 was e to the x, plus u2, so that's x minus 1 natural log x, times y2, which was x e to the x. Alright, and we take all of that, and remember finally that the solution y is equal to y sub h plus y sub p, and so the y sub h, remember, was c1 e to the x plus c2 x e to the x, and then plus, and I'm not going to write the whole y sub p, okay, where y sub p is this whole nasty thing. Alright, and so that's the idea for variation of parameters. Alright, so there's a lot in this section. There's two major methods, and you want to practice both of them and be aware of both of them. Alright.